Hello, my name is Nick Wolf, and this is the video presentation for the PokeStop Path Optimization project. This project was worked on by myself and Devin Doss. Before jumping into things, let's quickly highlight the motivation behind this project.
Dev, what are we doing out here? It's freezing.
There was a Mewtwo raid at this gym, and I still need a shiny. I never skip a nearby PokeStop. If only I knew the optimal path between them, I could have been done hours ago.
Have you ever heard of Garobi?
No, is that a Pokemon?
No, it's an optimization solver. Come on, let's go inside and I'll show you.
Okay, but one more raid.
While Devin's doing his raid, let's discuss how we went about finding the optimal path between Pokestops. The first thing we needed to do is decide exactly what an optimal path looks like in the scope of Pokestop interaction. We decided it was the path where we pass the maximum number of Pokestops and gyms in some designated period of time. Thus, we formulated the problem as a type of score maximization problem, where each Pokestop counts as one score point and each gym 2, since gyms can yield better rewards than normal Pokestops. With these specifications in mind, we needed a maximization algorithm that could take into account travel time between stops, as well as some sort of score system for the type of stop. It turns out we didn't learn about any problems like this in class, though it is a defined problem. It's sort of a combination of the traveling salesman and the knapsack problem, and it is commonly referred to as the orienteering problem. Having discovered an algorithm for the orienteering problem, we found a map and created a graph of the problem. We defined Pokestops and gyms as nodes and labeled the edges with the estimated relative distance between nodes, which we would later transform into estimated travel time between nodes. We defined the starting and ending nodes for the trip as Thompson Library and Mendenhall, since we are often at Thompson in the time leading up to ISE. Though a typical orienteering problem might have every node on the graph connected, we do not have the compute power nor the patience to hard-code each node-to-node distance, and thus only connected nodes which we thought made the most sense in the scope of traditional Pokemon Go exploration. Oh, sounds like Devin's back from his raid. I'll let him take over from here. How'd it go, by the way?
I got it.
Nice, man.
Alright, now let's dive into some technical details. The orienteering problem can be defined with the aid of a graph of vertices being the Pokestops and the edges being the paths between the Pokestops, each having its own time. We store these times in an array Tij, where element I, j is the time it takes to travel from I to j. On the map we drew, each path is given a number 1 through 13, but in our program, we multiply these values by 10 to convert into seconds. For example, if the edge between node I and j is 4, that means it takes 40 seconds to travel between the two nodes. Scores are associated with each vertex and stored in Si. Given these variables, the orienteering problem can be modeled as an integer programming model. Our decision variables used were xij and ui. Xij is 1 if a visit to vertex I is followed by a visit to vertex j, and 0 otherwise. Ui is the position of vertex I in the path. The constraints we used to structure our program were the following. Constraint 0, the objective function, is to maximize the total collected score. Constraint 1 guarantees that the path starts in vertex 1 and ends in vertex n. Constraint 2 ensures the connectivity of the path and guarantees that every vertex is visited at most once. Constraint 3 ensures the limited time budget. Constraints 4 and 5 are necessary to prevent subtours. These subtour elimination constraints are actually formulated according to the Miller-Tucker-Zemlin formulation of the traveling salesperson problem. Once we implemented the constraints, we tested our program with multiple different time budgets. For case 1, our usual case where we walk over to class from Thompson 4 minutes before it starts, we set our time budget to 240 seconds. Once we did this, our program found the path highlighted on the map. This path gives us a score of 11, letting us spin 9 Pokestops and 1 gym before we arrive at class. We had 2 other cases we wanted to explore, the first being if we're running late to class. We wanted to know the fastest path on our map, and we found that in 230 seconds, we could spin 6 Pokestops as we sprint across the oval. Our other case was if our homework was pushed back to Monday. If, by some miracle, we're actually leaving early for class, is there a path that takes us to every node? We found that in 640 seconds, roughly 11 minutes, we could travel from Thompson to Mendenhall while spinning every single Pokestop and gym on the oval, giving us a score of 18. While we were able to get our program to work, there are obviously a lot more PokeStops on campus than just the oval. We stuck to the oval out of the fear that our graph would grow exponentially and lose performance, but Garobi being the awesome
solver
that it is, this was no problem. In the future, we'd like to see this implemented with all of campus.